Okay. So thank you to everybody and to the Kavli Institute for allowing us to have this grant and start this research. So here, together with my collaborator, Kidan from the Root Lab, we are trying to answer a specific question. So how is it possible that a change in the type of transmitter expressed by few neurons can have an impact on behavior? And where does this question come from? Some of my previous research have shown that when a mouse is repeatedly exposed to the addictive drug penicillin, PCP, approximately 600 neurons in the prelimbic cortex that were glutamatergic gain the expression of inhibitory GABA. And indeed, when we permanently label those glutamatergic neurons using a specific mouse line, and then we treat mice with PCP, an immunostain for GABA, we can clearly see that there are neurons over here that are co-expressing GABA and mCherry. Not only, but this gain of GABA is also causally linked to the appearance of cognitive deficit, because when we treat mice with PCP, but we use an SH-GAD1 interference RNA strategy to prevent the expression of the GABA synthetic enzyme, now do you see that despite the treatment with PCP, we cannot detect cognitive deficit any longer. So now the question is, how it is possible that 600 neurons can create these change in behavior? So we figure out that there may be at least two ways, alternative or concomitant, in which this can happen. A possibility is that when a neuron is gaining GABA, you also undergo morphological reshaping, creating new axon branches and new synapses. And to answer this question, I've been working on finding a way to label the neurons that are gaining GABA and count branches and synapses. Another possibility that instead my collaborator Kidan is mostly working on is that the neurons that are gaining GABA are releasing this inhibitory transmitter, thus affecting the activity of the downstream target. And to answer this question, we want to perform in vivo calcium imaging in the target region upon stimulation of the neurons of interest. Now, to answer this question, the first step was to identify at least one of the regions where those neurons project. So my strategy was to first specifically label them and look throughout the brain for the presence of labeled axons. I did that using an intersectional strategy and a Cree-on flip-on mouse line, in which only in cells that express both Cree and flip, we will have a functional expression of channelrhodopsin and YFP. And I injected it in a mouse that expressed Cree under a glutamatergic marker and flip under a GABAergic marker. Now, when I was screening, as you can see exemplified here in this picture, in multiple mice, I noticed the presence of green labeled axon in the nucleus accumbens. That it's an interesting region for us because it's also involved in the response to drug of abuse. What, however, we didn't know was whether these neurons are actually projecting and synapsing, making synapses in the nucleus accumbens or not. And to answer this question, I decided to validate the target by injecting retrobeats. So here you can see an example of our injection site, and the retrobeats were injected in the same mouse line of before to permanently label glutamatergic neurons. Then we treat the mice to PCP, and then we can go and look in the prelimbic cortex, which are the cells that have uptaken the beats. And as you can see exemplified in the picture, we were able to detect neurons that have taken the retrobeats and then express both mCherry and GABA, so the glutamatergic neurons that are getting GABA. During this analysis, I also noticed that I failed to detect purely GABAergic neurons that were co-expressing beats, in line with the general knowledge that projection from the prelimbic cortex to the accumbens are mainly glutamatergic. Thus, I figured out that we can use a Cree-driven mouse line targeting GABAergic markers to specifically label those neurons. Now that we know that the nucleus accumbens is one of the targets, we can proceed to see what happened in this region. So to answer our first question and analyze the structure of the neuron, I decided to use this virus over here, a Cre-dependent virus that expressed TD tomato in the cell body and projection, and have synaptophysin fused with GFP to identify synaptic panta. The plan is to use it in both VGAT-Cre mice to selectively label the neurons that have gained GABA, or in VGlut1-Cre mice as a control to label glutamatergic neurons. I'm then gonna go and count the number of lateral branches and the number of synaptic panta between the groups. Despite the analysis is still on process, and I hope to give you the result of this difference soon, here you can see an example of a in two-channel picture of the nucleus accumbens of a VGAT-Cre mouse injected with our virus and treated with PCP. It's clear that the axon is clearly labeled by TD tomato. You can see a dimagnification, and it's that GFP is signaling the presence of synaptic panta. So I also would like to give you an idea of how we're planning to proceed and what we have done to answer our second question. So what happened at the activity in the downstream region? To perform in vivo calcium imaging, we revised our design and decided to use a VGAT-Cre mouse line and inject in the nucleus accumbens 3 different viral vectors, a retrograde Cre-dependent AAV expressing an excitatory auxin, the same, and a retrograde AAV that is the same of what I showed you at the very beginning, that will allow us to prevent the gain of GABA and the GABA synthetic enzyme, as well as a control virus. And finally, we can also use a non-Cre-dependent GCAMP to perform imaging in the accumbens. So you can see that after treatment with PCP, we will have that those neurons that were previously glutamatergic and are now expressing GABA are also expressing Cre, so are expressing our retrograde virus. And we can therefore proceed to, oh, sorry. Okay. I apologize, my computer is a little bit slow. So we can stimulate in the prelimbic cortex and then move to record from the nucleus accumbens. And we will have 2 different groups of mice. You can see we will have a group of mice treated with our control virus, in which the neurons that have gained GABA are still expressing GABA. And we will also have a mouse line in which the neurons that have expressed GABA have been forced not to express the GABA synthetic enzyme. And so we don't know what they are releasing, but definitely they cannot release GABA. And we expect that in this latter group, the activity in the nucleus accumbens will be increased as compared to the previous group. And to conclude, I would like to show you a test that my collaborator Kidan have done to image in vivo calcium imaging into the nucleus accumbens upon stimulation of channel rhodopsin. As you can see, there are these white flash that Kidan find out to be due to an oversaturation of the detectors on the 2-photon microscopy. And we are therefore now testing, as a way to solve this problem, the use of a red shifted opsin that can be stimulated with a yellow-green laser. So this is the state of our project at the moment, and I hope to give you, now that we have finished the troubleshooting phase, more details soon. And I would like to conclude by giving my sincere thanks to the Kavli Institute for awarding us this innovative research grant and allowed us to do this full of troubleshooting type of research. And my special thanks to my collaborator Kidan that cannot be attending today. And a special thank also to the Spitzer and Root Lab for the mentoring as well as the equipment. And thank you all for your attention.